Welcome viewers. Today our topic of discussion is photochemical smog. With the advent of industrial revolution, the mixture of gases and particles in atmosphere began to change. The primary reason for this change down through the centuries is due to the practice of venting the products of combustion and other fumes into atmosphere as a natural way to avoid the noxious effects within the buildings. Well, such changes were as a result of emissions from everyday activities, be it from industrial sources or from the transport sector. All these emissions have a profound influence on air quality, and one such impact is the smog formation. The term smog was originally coined by Dr. Henry Anthony Desvaux in the year 1905. It is caused by small particles of material which become concentrated in the air for a variety of reasons. Usually, smog is of two types. The first one is the reducing smog and the other one is the oxidizing smog. The reducing smog is caused mainly by combustion of coal and emissions of sulfur dioxide and dust. It is also called as London smog or grey smog and most commonly as industrial smog. However, since 1940s, a class of different smog pollution events with less clear origin has arisen around large cities. Unlike industrial smog, which is a mixture of smoke and fog having greyish combination of soot and sulfurous compounds and water vapors, this type of smog, besides being brownish in color, has neither smoke nor fog as its key components. Well, it's referred to as photochemical smog, as it is produced when sunlight acts upon motor vehicle exhaust gases. The term photochemical itself reflects the fact that this smog occurs due to the influence of strong sunlight and high temperatures on anthropogenic air pollutants like nitrogen oxides and volatile organic compounds. This airborne pollution was first observed in 1944 in Los Angeles, USA, where it was characterized by an atmospheric haze accompanied by irritation of eyes and lungs. Analysis of a sequence of these photochemical events gave the first indication that emissions from motor vehicles were a major contributor. Certain weather conditions such as temperature inversion intensifies the photochemical smog. As is seen in this figure, under normal conditions of daytime temperature is highest near the ground because sunlight strikes the earth and the absorbed heat radiates to the air near the surface. The warmer air near the ground rises, carrying the pollutants upwards and dispersing them at higher altitudes. At times, a warmer air layer occurs above the cooler layer. This condition of cooler air below and warmer air above is called temperature inversion. During cloudy weather, the sun is not strong enough to break inversion for hours or even days. One of the most harmful effects of inversion development is that it leads to strengthening of smog and also high accumulation of various pollutants close to the ground level, thereby increasing the health implications. Chemical pollutants in photochemical smog. Photochemical smog is a state that develops when primary pollutants, which are created from fossil fuel combustion, interact under the influence of sunlight to produce a mixture of hundreds of different hazardous chemicals known as secondary air pollutants. Some typical constituents of photochemical smog are volatile organic compounds and nitrogen oxides, which are primary pollutants. And some secondary pollutants are peroxyacetyl nitrates, ozone and peroxybenzyl nitrates. First, volatile organic compounds or VOCs. These are organic chemicals that are primarily compounds of carbon whose composition makes it possible for them to evaporate under normal indoor atmospheric conditions of temperature and pressure. These include propane, butane, methyl chloride, formaldehyde, acetone and toluene. However, these compounds exclude carbon monoxide, carbon dioxide, carbonic acid, metallic carbides or carbonates and ammonium carbonate. The sources of VOCs are paints, wood preservatives, aerosol, cleaners, disinfectants and moth repellents. Nitrogen oxides or NOx. These are the oxides of nitrogen that are formed as a result of anthropogenic activities like combustion of oil, coal, gas in both automobiles and industry, and natural activities like bacterial action in the soil or forest fires, volcanic action and lightning. All combustion processes account for only 5% of nitrogen dioxide in the atmosphere, most of which is formed from reaction involving nitric oxide or NO. As nitric oxide immediately reacts with additional oxygen to form nitrogen dioxide and nitrogen tetroxide, nitrogen dioxide absorbs light and is largely responsible for brownish color of photochemical smog. Peroxyacetyl nitrates or PAN, which is referred to as PAN. It is a secondary air pollutant having unpleasant odor. PAN causes eye irritation and has detrimental impact on lungs besides being highly toxic to plants. Nitrogen dioxide, oxygen and hydrocarbons from unburned petrol react in the presence of sunlight to produce peroxyacetyl nitrate. Peroxybenzyl nitrate or PBN. It is produced in photochemical smog when olefin and nitrogen oxide present in the atmosphere react together. This aromatic compound is a strong eye irritant, even 100 times more powerful than that of PAN and 200 times than formaldehyde. Ozone. Unlike the ozone in the stratosphere, which protects Earth from harmful UV radiation, the tropospheric ozone is harmful to life forms. The formation of oxidants, particularly ozone, when exceeds 0.15 ppm or more for an hour in atmosphere indicates the formation of photochemical smog. Ground level or tropospheric ozone is formed when nitrogen oxide, primarily from vehicle exhaust, and volatile organic compounds from paints, solvents and fuel evaporation interact in the presence of sunlight, which is called as photolysis. In the simplest term, ozone is formed by an atomic oxygen synthesizing with diatomic oxygen molecule and a third molecule acting as a stabilizer to take away excess energy. Let's see the steps involved in formation of ozone. Firstly, a hydrogen atom is formed by the reaction of carbon monoxide and hydroxyl radical. In turn, the hydrogen atom reacts with the surrounding oxygen to produce the peroxy radical. The peroxy radical reacts with nitrogen oxide to produce nitrogen dioxide. Nitrogen dioxide is photodissociated back into nitrogen oxide and produces atomic oxygen. Atomic oxygen formed in the previous reaction reacts with oxygen and the stabilizer molecule. So, the overall reaction is that a molecule of oxygen with an oxygen free radical, that is having unpaired electrons, makes an ozone molecule. Now, the factors for development of photochemical smog. For the commencement of the chemical processes in photochemical smog, the following conditions must occur. First, sunlight, then the production of oxides of nitrogen, then the production of volatile organic compounds, And lastly, the temperature should be greater than 18 degrees Celsius. If all these criteria are met, several reactions will occur producing the toxic chemical constituents of photochemical smog. Now let's see what happens to the atmospheric concentration of different smog constituents as a function of time of the day. As is seen in the generalized plot, shortly after dawn, the level of nitric oxide in the atmosphere decreases markedly, a decrease which is accompanied by a peak in the concentration of nitrogen dioxide. During the midday, the level of aldehydes and oxidants become relatively high. However, the concentration of total hydrocarbons in the atmosphere peaks sharply in the morning, then decreases during the remaining daylight hours. Besides the time of day, there are several other meteorological factors that can influence the formation of smog. These conditions include precipitation, that can lessen photochemical smog as the pollutants are washed out from the atmosphere with the rainfall. Temperature inversion can enhance the severity of photochemical smog episode. Normally, during the day, air near the surface is heated, and as it warms, it rises, carrying the pollutants with it to the higher elevation. As we have already discussed the impact of temperature inversion on smog, the pollutants can be trapped near the Earth's surface. The inversion causes the reduction of atmospheric mixing and therefore reduces the vertical dispersion of pollutants. Lastly, wind can drive photochemical smog away, replacing it with fresh air. However, the problems may arise in far-off areas that receive the pollution. Topography is yet another important factor influencing how severe a smog event can become. Communities situated in valleys are more susceptible to photochemical smog because hills and mountains surrounding them tend to reduce the airflow, allowing for pollutant concentration to rise. In addition, valleys are sensitive to photochemical smog because relatively strong temperature inversion can frequently develop in these areas. Now, the mechanism of photochemical smog formation. The first step in the photochemical smog formation is the reaction of nitrogen dioxide in the presence of sunlight to form nitrogen oxide and atomic oxygen. Then the oxygen molecule in the air reacts with the atomic oxygen and an energy absorbing third body to give ozone. Ozone and nitrogen oxide react to form nitrogen dioxide and oxygen. However, this later reaction is rapid and the concentration of ozone remains low until that of nitrogen oxide falls to even a low value. Production of organic free radicals from hydrocarbon is the third step. Here, atomic oxygen reacts with the hydrocarbon, giving out other products. Lastly, a chain propagation reaction occurs where branching and termination reactions take place. Usually, in this reaction, secondary air pollutants like peroxyacetyl nitrates are formed, and this constitutes the chain terminating process in the smog. Effects of photochemical smog. Smog influences human health, environment, and even causes property damage. Smog can cause or aggravate health problems such as asthma, emphysema, chronic bronchitis, and other respiratory problems such as eye irritation and reduced resistance to cold and lung infections. Many of the chemicals are highly reactive and oxidizing, which is bad for human health and inorganic matter. Photochemical smog is therefore considered to be a problem of modern industrialization. It is present in all modern cities, but it is more common in cities with sunny, warm, dry climates and a large number of motor vehicles. The products produced in the smog reaction, that are ozone and peroxyacetyl nitrates, degrade and heighten the negative environmental impacts. PAN is a powerful respiratory and eye irritant and very toxic. High concentration of it leads to damage to vegetation. The ozone in smog also inhibits plant growth and causes widespread damage to crops and forests. Volatile organic compounds or VOCs are known to have both short and long-term impacts on human health. For instance, eye, nose and throat irritation, headache, damage to liver, kidney and central nervous system. Some organics are carcinogenic for both animals and humans. Irritation of eyes, nose and throat and eye watering are the body's initial response to exposure to low photochemical smog concentrations. Acute exposure may progress into symptoms such as lung inflammation, decreased ability to breathe, increased susceptibility to respiratory disease, increased sensitivity to allergens, reduced athletic performance, chest tightness discomfort, pain while breathing deeply, triggering asthma attacks. Higher concentration due to prolonged exposure or cumulative exposure may result in increased risk of lung diseases, fibrosis which leads to less elastic lungs and loss of functional tissue, risk of permanent decrease in lung capacity, lung tissue damage and premature lung aging. Asthma, bronchitis, coughing and chest pain, increased susceptibility to respiratory infection, emphysema, decreased lung function and physical performance are some of the other impacts. The people who are more prone to the effects of smog are children, elderly people and people with impaired lung function. Children tend to spend more time outdoors, mainly in favorable weather conditions, that is during clear sky and warmer temperatures, which is when photochemical smog is more prevalent. As their body is still developing, thus their narrow internal airways have an increased risk of being obstructed. People who have asthma or emphysema are at risk because smog, especially ozone, further heightens the reaction in their air passageways. Individuals who exercise are also susceptible to negative side effects from photochemical smog. When exercising, one inhales larger quantities of air, which increases the amount of pollutants entering the body and further alleviates the impact. Hence, at the end of this lecture, we find that the booming economy has led to creation of vast suburbs and mushrooming use of vehicles for commuting to and from places. As the other fossil fuels are being used in place of coal for heating, industry and transportation, industrial smog is being largely replaced by another kind of smog called photochemical smog. It is produced when several pollutants from automobile exhaust like nitrogen oxides and VOCs are acted by sunlight. This brownish irritating haze usually occurs at places with warm and sunny weather, typically arising during morning commute and begins to dissipate only by the time of the evening commute. Meteorological and topographical factors have a profound influence on its location, duration and severity. Hence, the major constituents of photochemical smog are ozone, nitrogen oxides, peroxyacetyl nitrates and volatile organic compounds. All these chemical pollutants have both short and long-term impacts on the life forms, be it plants, animals or humans. That is all we have in this session. Thank you for watching.